In this video, we're going to be talking about the GCD Euclidean algorithm, the GCF, and then we're going to see how to implement this into our code. Okay, so let's start off. So what exactly is the GCD? Well, what we usually call the GCD, we might also call the GCF. So these are kind of interchangeable. And essentially what this means, or what it's defined as, is the greatest common. And depending on whether you use D or F, it's going to be divisor, or it's going to be factor. And these basically mean the same thing. And what it essentially just means is it's the largest number that can evenly divide two numbers. So let's look at a few examples here. So I'm going to erase this. Okay, so let's see a few examples. So if we take the GCD of, let's say, 6 and 8, well, what we're going to get, or what we should notice, is that the GCD is equal to 2. And the reason it's going to be 2 is because, let's think backwards, okay? So what is the greatest common divisor of these numbers? Well, it's going to be, at most, the minimum between the two numbers, right? So it's either going to be, or it's at most going to be 6. Well, in this case, it's definitely not 6 because 8 does not divide into 6. Then let's work our way down. Is it 5? Well, 8 doesn't evenly fit into, or 5 doesn't evenly fit into 8. Let's think about 4. Well, 4 does evenly fit into 8, but it doesn't evenly fit into 6. Then let's look at 3. 3 doesn't work. It only works for 6. Then look at 2. And for 2, we should notice that it's going to evenly fit into both numbers. So for 6, it's going to evenly fit 3 times. And for 8, it's going to fit in 4 times. Okay, let's look at a few more examples. So let's find the GCD of, let's say, 3 and 9. And well, in this case, what it's going to be is it's just going to be 3, because that's the greatest number that evenly divides both numbers. Okay, a few more examples. GCD of 5 and 7. And for this example, what we should notice is that none of the numbers will be able to do this except 1. So 1 is always going to be your lowest common divisor. Okay, let's look at 4, 1 and 4. So GCD of 1 and 4. This answer right here, since it's at most the minimum between the two numbers, and at minimum 1, in this case, it's going to be 1. And then finally, let's look at another example, like a slightly larger example of 18 and 24. In this case, it's just going to be 6. And you might be able to see that the greatest common divisor of these two numbers is going to be 6. Okay, so why exactly does this work? Okay, so let's look at exactly why this works. So what we're going to say is we're going to say, or for this algorithm, we know that we're trying to look for the GCD of A and B. And what we can say is that A is equal to BQ, some number Q, plus some remainder, right? You're going to try to put as many B's into A, and then you have some left over, which is your R. R can be equal to 0 or up to B minus 1, right? Okay. So what we're basically saying for this Euclidean algorithm is that the GCD for A and B is also equal to the GCD of B and R. So let's look at an example. So keep this in mind once again, what the Euclidean algorithm is saying. So once again, I'll write it up here a bit smaller. The GCD of A and B is equal to the GCD of B and dar. If we have the equation B is equal to, A is equal to BQ plus R. Okay, so let's look at exactly how this is going to work out. So let's take an example, a pretty large example of what is the GCD, and I'll use another color here, GCD of 2,322 and the GCD of 654. Well, in this case, this is going to be my A. So once again, we know this is my A, and this right here is going to be my B. So in this case, once again, we know A is equal to BQ plus R. So what we're going to do is we're just going to apply that formula, right? So we're going to apply this right here. We're going to say, in this case, 2,322 is equal to 654 times some number plus some other number, right? And I've already done these calculations ahead of time. So this is going to be 3 here, and this is going to be 360. So 654 fits into 2,322 at most 3 times, and it has a remainder of 360. And so what is our Euclidean algorithm saying? Well, it's basically saying that the GCD of this right here is going to be the same thing as the GCD of B and R. So what's B in this case? Well, in this case, B is once again just going to be 360, right? So, 654, right? And our R, right, that's the remainder, is 360. And so once again, we can apply this idea. So we can say 654 is equal to 360 times some number plus some other number. In this case, it'll fit it into ones, and the remainder is 294. Okay, now let's reapply the GCD function, right? Our Euclidean algorithm right here. And we're just going to say that this GCD right here is the same thing as the GCD between 360, right? This B right here, and the R, so 294. And what we're going to say is this is the GCD, this is 360 is equal to 294 times some number plus another number. And in this case, it's just going to be 1, right? And 66. Okay, now let's take this even further. So we're just going to say this GCD is the same thing as the GCD of 294, that's our B, and 66. And now we can say 294 is equal to 66 times some number plus another number. And so that number is going to be 4 and 30. Then we can say that the GCD, this GCD right here, is the same thing as the GCD of 66 and 30. And what we can say is that 66 is equal to 30 times some number plus some other number. And in this case, it would be 2 and 6. And then we can say that the GCD of this right here is equal to the GCD of 30 and 6. We're going to say that 30 is equal to 6 times some number plus another number. We can see that this is 5, and this is right here 0. We can go once more, and we can say that this is equal to the GCD between 6 and 0. When this number is 0, right, we know that it's just going to be equal to the other number, right? So we know that our final answer is going to be 6. And so therefore we can say that the GCD between 2,322 and 654 is equal to 6. Now you might be wondering, why exactly does this work? So why does this work? And basically how we're going to prove this is we're going to start off with our little claim here. So once again, our claim is that if, right, if A is equal to BQ plus R, then the GCD between A and B is the GCD of B and R. Right? And let me rewrite that, sorry, of B and R. Okay, so that's our little claim right there. So our claim, and we're just going to start off the proof with, and this is going to be a pretty quick proof. And if you're not really interested in it, it's not going to be too rigorous. So yeah. So we're going to start off with, once again, with A is equal to BQ plus R. And we want to say that the GCD between A and B is equal to D if and only if the GCD of B and R is also equal to D. Right? That's pretty much our claim. Okay. So what we're basically saying is D divides A and D divides B, right? Well, if D divides A and D divides B, what we can say is that D divides A, sorry, and let me extend this a little. D divides Q, A minus Q times B. And this is, you can prove this on your own time, but I'll give you a few little steps to take to kind of understand why this works. And we can basically come to this conclusion by basically saying, by noticing first, if D divides A and D divides B, then we can basically have D divides A plus B. And you can prove that. It's not too hard to prove. And what we should also notice is that if D divides A, then D divides CA for some A, for some C, sorry. Some C. And so if we, take this back to our formula of A is equal to BQ plus R, then what we can do is we can essentially write R. So from here, from here, we're going to rewrite R as equal to A minus BQ. And you can see that's the same thing as A minus QB. It's simple multiplication. And so now what you can basically say is that D is a common divisor, right? So since we have this, we know that D is a common divisor between B and R, right? So there's that. Okay, so that wasn't too rigorous of a proof, I know, but it was just a little introduction on why it kind of works. And you can kind of prove this on your own time if you're interested, but that's that. Okay, let's jump into some code. Okay, so now I'm in my IDE, and I'm going to show you guys how to code this up. So before that, we're going to see that in my sample input, I have an integer n as my first line of input, and this is going to be the number of test cases that I have. And for each test case, I want to find the GCD between the two numbers. So I want to find the GCD between 6 and 8, 3 and 9, 5 and 7, 1 and 4, and then 18 and 24. And I should expect 2, 3, 1, 1, and then 6 as my output. Okay, so let's start. So the first thing I want to do is I want to take in the number of test cases that I have. And one simple way of looping through test cases is simply by doing t minus minus, and then you're going to keep doing this while it's greater than 0, right? That's as long as you don't care about the number of test cases or the iteration that you're currently on. It just matters that you're going through the test cases. Then from there, I want to take in input for my A and B. Like so. And finally, what I'm going to do is I want to print out some GCD between A and B. And I'm going to have a function that returns it for me. One thing that you might have noticed is that the GCD function was almost recursive in nature, right? You were kind of building down, you were kind of going down, down, and down until you finally found a very simple answer, our base case when b is equal to 0. And what you should have noticed is that the answer of the current GCD call is the answer to the previous GCD call, right? And so by building that up, we realize that it's recursive. So what we're going to do is we're actually going to create a recursive method called GCD, pass in A and B. And once again, our base case is if b is equal to 0. Remember at the end, we finally found out that we had the GCD between 6 and 0, and then we just returned the 6. Well, that's basically what we're doing here. When b is equal to 0, simply return A. And then otherwise, what we have to do is we just need to return the GCD between b and r. So what exactly is b? So b is just the previous b, right? That's just exactly what was the previous number that we had, right? That's this b right here. Then we want the remainder. And the question is, how do we return that remainder? One way we can simply do the remainder is just by doing a mod b. Sorry, a mod b. And what a mod b does is it just generates, or it just returns the remainder when you divide a by b. So it's as simple as that. So let's run this program to see if it works. And as you can see, it fully works. Awesome. Okay, so the order actually doesn't matter between A and B. So I can switch these up and they would still give me the same result. So I just change this to 1 and 4, 7 and 5, and it'll give me the same result. So there you go. Okay, so you've heard of the GCD, but you might have also heard of the LCM. And the thing with the LCM is that it's actually quite simple to find out, right? What is the lowest common multiple of these numbers, right? What's the biggest number? That is a multiple of these numbers right here, right? What is the lowest common multiple? One easy way we could do this, and one simple way is you should notice, and first let's actually create a method called LCM between A and B. What you should simply notice is that one of the multiples of, or one common multiple between A and B is just A times B, right? A times B is a multiple of A and B. But what is the least common multiple? What is the lowest common number between these two? Well, what we can do is just divide it by the GCD between them both. And what that's going to do is that's going to reduce that number down until it's the lowest common multiple of A and B. And so I'm going to get wrong answer here, but what I'm also going to do is print out what is the least common multiple between A and B. And if we compile and run, we should notice that the lowest common multiple between 6 and 8 is 24, between 3 and 9 is 9, between 7 and 5 is 35, between 4 and 1 it's 4, and then between 18 and 24 it's 72. Okay, so here's the code for the GCD and LCM. So in this video, you learned about how to calculate these both, a little bit of a proof on how to do them, and that's pretty much it.